Okay, so the only thing I want to discuss now are some of the subtleties about when we went to the box, and perhaps you want to take the limit that the box becomes infinitely large. And there's a few ideas here that I think it would be worth making explicit. So I'm going to phrase this. Let's imagine that we want to take the infinite size limit of the box. And remember, our box had a length of L, so we want to consider the situation where L goes to infinity. Well, the kinds of things that we expect is that the Kronecker delta, delta k primed, will go into the Dirac delta distribution. And just as some notation, sometimes I will also write the Dirac delta with that little 3 subscript. Okay, these two mean the same thing. It's just some idiosyncrasy of my own notation. Those two really mean exactly the same thing. I'll never take them to mean something different. Then discrete sums over k in the box will go into integrals over continuous momenta. Now, there's a few things going on here that I want to make explicit. And to make them explicit, I want to compare two equations, okay? So let me tell you what those two equations are. So the first one is we have a sum over k, delta of k, k primed. And because we sum over all possible momenta, that sum is just 1. So very good, no problem. Then the analog of this in the infinite volume limit, we would have an integral over these continuous momenta, a delta of k minus k primed equal to 1. Okay, let's just start to assign some dimensions to various things. Now, remember that we are working in units with h bar is equal to c is equal to 1. In that case, momenta are inverse lengths. So d3k will be length to the minus 3. Since 1 is dimensionless, we immediately learn that the delta function, the Dirac delta, must have dimensions of length cubed. When we look at the discrete formulation, well, here we have the Kronecker delta. And how is the Kronecker delta defined? Well, delta k prime, its value is 1 if k is equal to k primed, or it's 0 if k is not equal to k primed. Well, 1 is dimensionless. That means that the Kronecker delta is dimensionless. And when we're summing just over these discrete numbers, that sum, of course, is just an instruction to add numbers. It's also dimensionless, and the 1 is dimensionless. So what you can see is the replacement that we made to go to the infinite box limit. What has it done? By replacing the Kronecker delta by the Dirac delta, you've gone from something that was dimensionless to something that is dimensionful. And by going from the sum to the integral, you've gone from something that is dimensionless. So on this side of the page, things are dimensionless. And on this side of the page, things are dimensionful. So at very least, you should realize that there are some things going on that perhaps you weren't aware of. So let's discuss the differences between these. I should also say on this side, all of the labels are discrete. And on this side, all of the labels are continuous. And a lot of what's going on is related to whether the label is discrete or continuous. And well, we'll see all of that working. So to set up the discussion, I want to consider the hydrogen atom. Okay, so let's study the hydrogen atom. So why is the hydrogen atom a good system to study? Well, I want you to remember, what does the potential of the hydrogen atom look like? So I'm going to plot V of x as a function of x. And it's this very deep well that's also very, very broad. Okay, it goes off like that. So there's two types of states that we can have. We could have states which are free at infinity. They can actually get free of the potential. These can be labeled by whatever momentum they have at infinity, so some momentum k. And in particular, they have a continuous label. And they have an energy which is greater than naught. They're free states, they're not bound. But then we can also have states which are bound to the potential, okay? So they cannot get free, they live in the potential. This could be the state with n is equal to 1, n is equal to 2, n is equal to 3. So all of these states have a discrete label. They're labeled by some integer. They have energy less than naught, so they are bound states. Continuous, let me say label. Okay, so this is the analog. So all of the continuous type states are sort of the things that you get after you took the limit that L went to infinity. And for the bound states, these are like the kinds of states that you had before you took L to infinity. So if we learn how to think about the continuous states and the discrete states in the hydrogen atom, we're going to be learning something about the difference between states that are inside the box and inside the finite box and states that are inside the infinite box. When we look at the continuous states, when we normalize them, we would have K, P, and this would be normalized to the Dirac delta distribution, okay? Now, you can do dimensional analysis and work out what then is the dimension, for example, of the ket P, and it's not dimensionless. It's got dimension of L. What is it? So this is 3 delta functions. So this would be like an L cubed. So this will have a dimension of L to the 3 over 2. If you take a discrete state, say something with energy level n and something with energy level m, this is normalized to the Dirac delta function. And that means that the state labeled with a discrete number is actually dimension of L to the naught. So they're different objects and we would use them in different ways. If you have a state which is normalized, then if you work out what is m, the overlap of bra m with ket psi, this is the probability amplitude to find the particle in state m. And the probability is just given by the square of the probability amplitude. So this is the probability to be in state m. If we take some k psi squared, well, we know that psi is dimensionless because it's normalized to 1, but we also know that the continuous label state is not dimensionless because it's normalized to the Dirac delta function. It has dimension of k to the 3 over 2. So the square of this thing, this has got dimensions of length cubed. What this is a probability density. So density is the important word there. And in fact, if you want to get a probability, to get the probability, you need to integrate the density over some domain D and D3K. So the D3K will have dimensions of length to the -3. The mod of k with psi squared has dimensions of length to the 3. So indeed, this is length to the naught, which is what we want for a probability. And what probability is this? This is the probability to catch the particle with some momentum in D, because D is some region of momentum space that we are integrating over, and we're now calculating the probability to catch the particle with some momentum in D. So these states with a continuous label are very different to states with the discrete label, and we would use them in a different way when we want to make a prediction. I just wanted you to be aware of that. And that brings us to the end of this chapter.